Okay, the final bit of the analysis is we're going to look at analysing how the inputs affect the outputs. If you're looking at the data, it's quite easy to find out about special causes. So you look at what has happened in that period. So you can see the points that are out of control, and you can go and say what happened then, and you're pretty likely to be able to find it out. It's quite relatively straightforward. What's more difficult is to understand the common cause. So which things influence which other things. And you might have some idea, but you need to have some evidence to support that idea. So we're going to focus on common cause investigative strategies. So first thing you do is to stratify. So is to see if you can find categories by which you could say, well, this category is more likely to produce a higher level of my outcome or a lower level of my outcome. So for example, if you've got a complicated product, let's say that, so you're printing something with two colours rather than one colour, you could say, well, let's compare my my runtime with the one colour product and a two colour product. You see, is there a difference, statistical difference between those two things? The other thing you should do is to disaggregate, so you can go down a level or up a level sometimes to identify what might be potential causes. So, for example, if you're looking at monthly output, monthly throughput, let's say, for example, you might not see very much. But if you looked at a daily level, you might start to see some patterns. Or if it's a shift level, you might see some more interesting patterns. So we can start to move up and down the hierarchy of your process to try and work out if you can find out if there are other things going on to do that. When we're looking at this category thing, the best thing to do is to use what we call a box and whisker plot. So a box and whisker plot is actually a distribution. So if you think about the middle line in the box, it is the mean line, pretty much, and then the box, right, is the fat bit of the curve. So it's the middle bit of the curve, and then as the curve starts to tail off, the tails of the distribution are those whiskers. And then sometimes when you've got like things that are even outside that, you get these little crosses. So things that don't lie within the distribution. So you can see the normality, you can see the scale of the thickness of the distribution. But what's really important is that you can then compare one category with another. So on the right-hand diagram, you can see, well, actually, I can tell that on the right-hand side, those two categories are have got a different mean than the other categories. You can see the size of the variation is different as well. And one of the useful things about this box and whisker plots is it's visual, and you don't necessarily get sidetracked by looking for something that's statistically significant. So you might have a mean of 50 on one product. Let's say we're talking about OTIFs, you might have a mean of 50 on one and a mean of 52 on another. So that's statistically different, but if you've got a target of 70% OTIF, it's not practically significant. So it helps you frame what's important and what's just trivial statistics, okay, because it's visual. If we've got a number, all right, then we could then compare the number and how it varies with the outcome. So as long as you can measure the outcome, obviously. So this example is measuring sales versus advertisements. So you could say that the number of advertisers increases my sales. But it doesn't necessarily mean that. It means they vary at the same way, the same rate. So that it might be the products that as you sell more, you've got more money to invest in advertising, for example. So it's a relationship, but not a causal relationship. But if you, in your causal framework, if you said, well, actually, that I believe that batch size, if batch size increases, then flow efficiency decreases, the amount of elapsed time it takes. Then if you've got some evidence, then that would support your argument. You've got both logic and evidence. So you're moving towards something that you can say with a degree of certainty. Just going off the data alone does not suggest that is causal, but it helps you prove whether your initial idea was right or not, and the extent to which it varies. So you draw a line, and the steepness of the line tells you the strength of the relationship. So if that line was very flat, it was a very small incline, that would say, well, pretty much it does vary a bit, but it's not very much. So the steeper the line, the more significant impact, or the significant variation in the input with the output. Okay, you can use regression, so you can put what's called an R-squared line in. The line is calculated on some fancy statistics. The problem is that you're better off drawing the line yourself. If you let the software draw the line, it will draw a line regardless. So it might draw a line on there, which is its best fit line, but it might not be related to the data whatsoever. From a practical point of view, it has to draw a line, it will draw a line. So you're better off not doing that, you're better off doing it yourself with a ruler and a piece of pencil. So what we're trying to get at here is that if you can't see it, right, it's not there. It might be statistically significant, as I said before, but not practically significant. So if you've got like a scatter diagram where you're comparing a number input with an output, and it's all over the place, then move on, because it's obviously not having a major impact. And correlation is not necessarily causation. So you've got to have some logic behind that. So what you end up doing is having some logic, and sometimes that logic is specific to your business, and sometimes it's generic. So like we said before, if you've got a product where the larger the batch size, the longer it takes to run on the machine, okay, then that's a generic logic. Or if you've got a specific logic where you know that one of your products runs with at a higher speed than another because of a specific reason, then you can prove that. And if you've got evidence from your data that that's occurring, then you can tie those two things together, and you can have what we call a hypothesis on probation. So nothing's ever quite true, but it's true enough to do something about it. And sometimes it might take you a bit of time to go through that loop. You might go through it a couple of times where you're trying to marry up the data, the evidence, with your logic, with your idea. And at a certain point you go, I've done enough, I need to move on. What we call the Captain Nemo approach to analysis. A couple of things to bear in mind from an advanced point of view is that there's something called statistical capability, which helps you set intelligent targets. So if you look at your variation, if you have a target that's inside plus or minus 3 sigma, then you're going to hit it some other time, just because your common cause variation says you're going to hit it some other time. So really you should have a target on your mean, because if you want to improve something, then you need to move the mean a whole distribution. Okay, there's quite a lot of you can look some of this stuff up, but it's worth thinking about when you get into setting targets, set intelligent targets that either you've got a chance of hitting at some point, or set the target such that you're not going to hit it by chance alone, which is you're kind of fooling yourself in that sense. The other thing to bear in mind is that how good your measurement system is. So when we came to do visit 1, we looked at the measurements you were doing, and we had an estimation based on what you were saying about whether we thought there was a risk of the measurement system being not good enough. And what that means is that the amount of variation in the way you measure it is as significant as the variability in the process itself, which means you can't really see the wood for the trees. So if I was in a room and you wanted to measure, gauge people's height by looking at them, right, then the chances are that the way we measured it would be quite variable, okay, person to person. Even if I did it twice or 3 times, a lot of variation there between, let's say, 5 foot or 4.5 foot and 6.5 foot, which is as much as a variation that you would find in a normal room of people in terms of their height. So in that case, the measurement system would not be good enough, and we would need to know that before we did any analysis. If you think this is the case, then you need to look very carefully at how you do that. It's not something that you can just pick up a book and do. It takes a bit of thinking about, and sometimes some specialist software.